When most people imagine the most dangerous predator the ocean has ever produced, they think of Megalodon. They're not thinking far back enough. The ocean is nearly 4 billion years old. Megalodon arrived late, within the last 20 million years or so. A blink in the scale of deep time, and before it got there, something else was already in charge. In fact, many things were, one after another. Over hundreds of millions of years, the ocean kept producing apex predators and then erasing them. There were reptiles, not fish, not sharks, but reptiles that grew to the size of a city bus, crossed entire oceans, and hunted in open water where there was no coastline to retreat to. Animals so large that a great white shark would have been prey, not competition. There were creatures whose reconstructed bite force rivals or exceeds anything that came after them, built not for speed but for crushing. And there was a moment, a long moment, millions of years when sharks almost completely vanished from the ocean, not declined, not struggled, functionally gone, and something else moved into the space they left behind. Each of these animals ruled, each of them was eventually replaced. And the pattern of how that happened, how the ocean keeps resetting its hierarchy, is one of the stranger stories in the history of life on Earth. Megalodon is the name everyone knows, but it was not the beginning of this story. It was closer to the end. Tonight, we go back further, to the predators that came before it, the ones most people have never heard of. But before we continue, let me know in the comments if you have any topic suggestions you would like me to cover in future videos. If you're the kind of person who finds this fascinating rather than dry, this channel was made for you. A like and a subscribe, keep it going. Now let's go back, long before Megalodon, to when something else owned the deep. Time in the ocean does not move as a line, but as a slow turning cycle, where dominance rises, settles, and fades, leaving space for something else to take shape. Across the last 450 million years, the position at the very top has never belonged to a single lineage for long. It has been filled, emptied, and filled again, not once or twice, but many times, each occupation shaped by the conditions of its moment. The idea of a permanent ruler does not exist here. What exists instead is a shifting role, defined less by the animal itself and more by the world that allows it to exist. An apex predator, in its simplest form, is an animal that reaches adulthood without being hunted by anything else, occupying the highest level of its food web. It feeds on others, but is not fed upon, and through that position, it quietly influences everything beneath it. Its presence alters movement patterns, population sizes, and even the physical spaces where other animals can safely exist. This role is not ornamental, it is structural, a point of tension that holds the surrounding system in balance. That position behaves less like a seat of power and more like a pressure point within the ocean's living network. When occupied, it shapes the flow of energy through the system, guiding how life distributes itself across depth, distance, and time. When vacated, the absence is not gentle. It sends a ripple downward, changing behaviors, opening niches, and allowing new forms to expand into spaces that were once restricted. Over long stretches of time, this constant reshaping becomes the defining rhythm of marine life. To understand this sequence, the scale must widen. The ocean itself has existed for about 3.8 billion years, forming long before complex life began to move with intent. Predatory animals, those capable of actively seeking and consuming other organisms, have been present for roughly 540 million years. Within that immense span, the story that follows occupies only the last 450 million years, a fraction of the ocean's total history, yet dense with transformation. Each segment of that history unfolds within a different version of Earth. Continents drift into new arrangements, opening and closing seaways. Ocean chemistry shifts as gases enter and leave the atmosphere. Temperatures rise and fall over millions of years, altering circulation patterns and nutrient distribution. In each of these worlds, the conditions select for a different kind of dominance, and so the apex predator changes with them, never repeating in exactly the same form. There is a pattern that threads quietly through all of it. When an apex predator disappears, it is not replaced through direct competition. It is removed by forces outside the living system itself. Climate shifts redraw habitats. Volcanic activity alters the chemistry of air and water. Asteroids deliver sudden irreversible disruption. The dominant animals of each era are not defeated by rivals. They are overtaken by changes in the world that made them possible. Recognizing this pattern reveals something deeper about the nature of extinction and prepares the ground for understanding the final disappearance that will come much later. What remains of these animals is fragmentary, bones pressed into sediment, teeth scattered across ancient seabeds, faint impressions left behind in soft layers that hardened over time. From these pieces, size, behavior, and even motion are inferred with care. Every reconstruction carries uncertainty, a range rather than a fixed point, and that uncertainty is part of the story itself. If the sequence is followed backward, past the familiar outlines of sharks and whales, past the forms that resemble anything alive today, it arrives at a world almost unrecognizable. Around 450 million years ago, the ocean held a predator unlike anything that would come after it, a creature without a jaw, without a spine, and without any living descendants. Its shape belongs entirely to its own time, and in that distant water, it marked the first occupation of a role that would never remain still. Long before bone, before teeth, before any animal could close its mouth around struggling prey, the ocean held a different kind of ruler, one shaped by softness and pressure rather than speed and force. In the Ordovician period, between 488 and 443 million years ago, the seas spread wide and shallow across the continents, warmed by a climate that favored abundance over urgency. Life filled these waters in layered stillness, drifting, anchored, or slowly crawling, with no large vertebrate presence to disturb the balance. At the center of this quiet dominance moved Carboniferous, a cephalopod, unlike anything that would follow it in form or lineage. Its body extended within a long, straight shell, a rigid cone that could reach between 6 and 9 meters in length, making it the largest known animal of its time. The shell itself was divided internally into chambers, each one subtly adjusted with gas and fluid to maintain buoyancy, allowing the animal to hover or rise with controlled ease through the water column. At the open end of this structure lived the animal itself, a soft-bodied organism equipped with a ring of grasping tentacles and a beak capable of crushing resistant surfaces. Movement came through a muscular siphon, expelling jets of water that pushed it forward in measured bursts. This was not the continuous swimming seen in later predators, but a sequence of controlled surges, each one repositioning the animal within a world where most life could not move freely at all. Its sensory advantage was as significant as its size. Carboniferous possessed eyes, and likely the ability to coordinate them in a way that provided depth perception. In an ocean where many organisms lacked even basic visual structures, this capacity introduced a new way of interacting with the environment. Movement could be tracked, distance estimated, and approach refined with intention. The water was no longer a uniform field, but a space with direction and possibility. Below, the seafloor stretched in dense communities of invertebrate life. Crinoids lifted their feathered arms into passing currents, filtering particles with patient repetition. Brachiopods remained anchored, opening and closing in slow rhythms. Trilobites moved across the sediment, armored and segmented, yet limited in speed. Together they formed a vast, slow-moving field of biomass, a living surface that extended across shallow continental shelves. Among them existed the earliest vertebrates, small jawless fish that stayed close to the bottom, protected by armor and guided more by instinct than by pursuit. They did not hunt in the way later animals would. They fed passively, drawing in organic matter, surviving within narrow limits. In the presence of Carboniferous, they were not competitors, but part of the available field of life, subject to a predator that moved above them with a different set of capabilities. For tens of millions of years, Carboniferous occupied this position without challenge. It had no natural predator. Its size, mobility, and sensory reach placed it beyond the constraints that shaped other organisms of its time. The ocean adjusted around it, not through resistance, but through accommodation, as life continued to expand beneath a presence that defined the upper boundary of possibility. This balance did not break through rivalry or gradual displacement. It shifted with the planet itself. Toward the end of the Ordovician, global conditions began to change. Cooling spread across the Earth as glaciation intensified, drawing water into expanding ice sheets and lowering sea levels across vast regions. The shallow seas that had supported dense invertebrate communities receded, exposing habitats that had existed for millions of years. As those environments collapsed, so did the networks of life they sustained. Approximately 85% of marine species were lost during this interval, including the great orthoconic nautiloids that had once moved through open water with quiet authority. Carboniferous disappeared along with them, leaving behind only fragments preserved in stone, silent records of a form that had no continuation. In the absence that followed, the highest position in the ocean remained unoccupied for a time, not as a pause, but as a condition awaiting a different solution, one that would arise from a change not yet seen. The next transformation does not arrive as a creature, but as a mechanism, small at first, almost unnoticed, yet capable of altering every interaction that follows. In the waters of the Silurian period, between 443 and 419 million years ago, a structural change begins to appear within certain fish, a hinged connection at the front of the head that allows movement in a way no earlier animal could achieve. It is simple in form, a pair of opposing elements that can open and close, yet within that motion lies a new kind of control over the surrounding world. Before this development, feeding was limited by constraint. Animals drew food inward through suction, filtered particles from passing currents, or seized what they could with flexible appendages. These methods allowed survival, but they did not allow decisive action against large resisting prey. Movement could bring an organism close, but there was no reliable way to secure, break, and consume something that struggled to escape. The ocean, for all its diversity, remained governed by interactions that favored opportunity over force. With the arrival of the jaw, that balance begins to shift. The ability to bite introduces pressure, direction, and intent. A closing structure can hold, crush, and process, turning feeding into an active pursuit rather than a passive encounter. The animals that first carried this feature were not yet dominant. They were small, varied in form, and likely used their jaws to handle modest food sources, scraping, nibbling, or sifting through material that required more precision than earlier methods allowed. The change, however, did not remain confined to that initial purpose. Over a relatively short span of geological time, the presence of jaws begins to reshape entire communities. Fish that possess this structure diversify rapidly, exploring different ways of using it, strengthening it, refining it, integrating it into bodies that can move with greater speed and coordination. By the time the Devonian period unfolds, from 419 to 359 million years ago, these animals have expanded into nearly every available niche, filling rivers, coastal shallows, and open waters with forms that vary in size and behavior, yet share a common advantage. Among them, one group rises with particular prominence. The placoderms, armored fish with bony plates covering their heads and upper bodies, become the defining presence of this era. Their designs range widely, some resting along the bottom with flattened bodies, others moving through the water column with a more streamlined shape. Sizes extend from small individuals, scarcely longer than a human hand, to large forms approaching 10 meters, each variation carrying the same fundamental innovation at the front of the head. The presence of jaws does more than enable feeding. It alters the relationship between predator and prey at every level. Animals that were once relatively secure within their environments now face a threat that can pursue, seize, and break through resistance. In response, new strategies begin to appear. Protective coverings grow thicker, movement becomes faster and more erratic, and patterns that disrupt visibility start to emerge. The ocean enters a phase where adaptation is no longer optional, but continuous, driven by a pressure that did not previously exist. Within this unfolding system, certain placoderms push the limits of what the jaw can achieve. Their structures become reinforced, their movements coordinated with a precision that allows sudden controlled closure. Among these, one form stands apart, not because it possesses teeth, but because it does not. Its biting surfaces are extensions of bone, sharpened through use, aligned in a way that concentrates force with remarkable efficiency. The absence of teeth does not diminish its capability. It refines it, producing a mechanism that can generate immense pressure without the need for replacement or regeneration. In this way, the jaw does not settle into a single design. It becomes a foundation for variation, capable of supporting forms that differ widely, yet share a common principle. What began as a modest structural adjustment evolves into a defining feature of vertebrate life, setting the stage for interactions that will continue to grow in complexity. Within the Devonian waters shaped by this change, one placoderm carries this development to an extreme, combining a toothless design with a force unmatched among fish, a presence that embodies the full potential of the jaw in a way that will not be repeated in quite the same form again. There is a moment in the Devonian when form and force align with unusual precision, producing a predator that seems engineered not through gradual refinement, but through a convergence of extremes. Dunkleosteus terrelli moves within this interval between 380 and 360 million years ago, carrying a structure that appears heavy and deliberate, yet functions with surprising speed. Its length reaches between 8 and 10 meters, its mass approaching 4 tons, yet the defining feature is concentrated at the front, where bone replaces what later animals would achieve with teeth. The head is enclosed in thick interlocking plates, fitted together like a rigid shield that protects the most vital mechanisms within. Behind this armored section, the body transitions abruptly into softer tissue, flexible and unprotected, a contrast that has shaped how it is preserved. Most remains consist only of the head, the rest having dissolved back into the sediment long before fossilization could capture it. What endures is the part that mattered most, the structure that delivered force. Where teeth might be expected, there are instead sharpened edges formed directly from bone. These blades meet along precise surfaces, each closing motion grinding them against one another, maintaining a continuous edge through use alone. There is no cycle of growth and replacement, no need for regeneration. The act of feeding preserves the tool itself, keeping it honed without interruption. When the jaws open, they do so with remarkable speed, completing the motion in roughly 20 milliseconds. This rapid expansion creates a sudden drop in pressure, drawing water and anything suspended within it toward the mouth. Prey is not simply seized, but pulled inward before its body can register the change. The closing motion follows immediately, bringing the bony edges together with a force estimated between 4,400 and 7,400 newtons at the point of contact. The absence of teeth does not reduce effectiveness. It concentrates it, channeling energy through a narrower interface that breaks through resistance with direct efficiency. This mechanism operates within a system that does not distinguish between prey types. Evidence preserved in fossil deposits shows fragments of Dunkleosteus itself within regurgitated material, partially digested plates, and bone sections that match its own structure. The pattern indicates that individuals consumed others of their kind, not as a rare occurrence, but as part of a broader feeding behavior that reflects the absence of constraint at the top of the system. Around it, other fish continue to evolve, including early sharks such as Cladocelidae. These forms move with greater flexibility, their bodies supported by cartilage rather than bone, their size limited to 1 or 2 meters. They occupy the same waters, but not the same position. Their role remains beneath the armored dominance of the placoderms, which define the upper boundary of predation throughout this period. For approximately 20 million years, Dunkleosteus and its relatives maintain this position without interruption. Their presence shapes the distribution of life, influencing where smaller animals move, how they feed, and how they avoid contact with a predator that combines protection, speed, and force within a single structure. The Devonian Ocean during this time carries a distinct character, one defined by heavy forms and decisive interactions, where the mechanics of feeding have reached a level of efficiency not previously seen. Yet within this stability, subtle changes begin to take hold. They are not visible in a single moment, nor confined to a single location. Shifts in chemistry alter the balance of nutrients, affecting the smallest organisms first. Variations in temperature influence circulation, redistributing oxygen in ways that do not immediately disrupt large animals, but begin to reshape the foundation beneath them. These adjustments accumulate slowly, spreading through systems that depend on consistency. As these changes continue, their effects begin to align, reinforcing one another rather than remaining isolated. What had been a stable arrangement starts to lose its equilibrium, not through conflict among its inhabitants, but through a transformation in the environment that sustains them. The conditions that supported the dominance of placoderms begin to narrow, and the ocean that once held them in balance starts to move toward a different state, one that will not sustain them in the same way. The change begins far from the water, in a place the ocean does not touch. On land, surfaces that were once bare begin to fill with structures that rise upward and reach downward at the same time. The first forests spread across the continents during the late Devonian, between 375 and 359 million years ago, forming networks of trunks, leaves, and roots that anchor themselves into rock that had never before been penetrated in this way. The transformation is gradual, but its effects extend outward in quiet, continuous motion. As roots push into stone, they fracture it, breaking apart minerals that had remained locked in place for millions of years. Rain carries these newly released elements into streams, then into rivers, and eventually into the ocean. Among these materials are phosphorus and nitrogen, nutrients that dissolve into the water and move through it with increasing concentration. What begins as a slow release becomes a steady influx, spreading across coastal environments and into shallow seas. Within these waters, microscopic organisms respond first, Algae begin to multiply, drawing on the abundance of nutrients now available. Their growth accelerates beyond previous limits, forming dense blooms that stretch across vast regions. At the surface, these blooms alter the clarity of the water, thickening it with suspended life. When the algae die, they sink, and as they decompose, they draw oxygen from the surrounding water, consuming it in quantities that outpace replenishment. This process unfolds not in a single place, but across multiple regions, repeating as nutrient flows continue. Oxygen levels decline, first in localized zones, then across broader areas, creating conditions where many marine animals can no longer survive. These regions, depleted of oxygen, expand slowly, merging into larger zones where movement becomes restricted and life begins to thin. At the same time, the forests continue to alter the atmosphere. As they grow, they absorb carbon dioxide, reducing its concentration in the air. This shift affects global temperature, initiating a gradual cooling that leads to glaciation. Ice begins to accumulate, drawing water away from the oceans and lowering sea levels. The shallow seas that once supported dense and varied ecosystems begin to contract, exposing areas that had long been submerged. The combined effect of these changes is not immediate. It unfolds over approximately 20 million years, in pulses rather than a single event. Periods of relative stability are followed by further declines, each phase reinforcing the last. Marine life adjusts where it can, but the scale of change exceeds the capacity for adaptation in many species. Reef systems, which had provided structure and productivity within the ocean, begin to collapse. These environments, built over long spans of time, depend on stable conditions, clear water, and consistent chemistry. As oxygen levels drop and temperatures shift, their foundation weakens, and they disappear from large portions of the marine landscape. Their absence removes a central support for countless species that depended on them for shelter and feeding. The loss spreads upward through the system. Approximately 70 to 80% of all marine species vanish during this interval, leaving behind a reduced and fragmented community. Among those lost are the placoderms, the armored fish that had dominated the Devonian seas. Every species within this group disappears. The lineage, which had persisted for around 50 million years, leaves no direct continuation. Dunkleosteus is among them. Its structure, once aligned so precisely with the conditions of its time, no longer fits within the changing environment. The mechanism it carried does not vanish entirely. The concept of the jaw continues, inherited by other fish that had existed in less prominent roles. These survivors, smaller and more adaptable, begin to occupy the spaces left behind. Sharks persist through this transition, not through dominance, but through flexibility. Their bodies require fewer resources to maintain. Their reproduction produces fewer but more developed offspring, and their forms allow them to move through a wider range of conditions. They do not rise immediately to the top. They remain, enduring through a period that removes larger and more specialized animals. What emerges from the Devonian is an ocean altered at its foundation. The structures that once supported dense life are absent, and the largest predators are gone. The uppermost position remains unfilled, not as a void of inactivity, but as an open condition shaped by a world that has not yet stabilized into its next form. The label suggests clarity, yet the reality it describes feels unsettled, as if the ocean is trying on forms without committing to any one direction. The Carboniferous period, from 359 to 299 million years ago, is often called the Golden Age of Sharks, a phrase that implies dominance and stability. What unfolds instead is a phase of experimentation, a widening of possibilities rather than a consolidation of power. With the armored rulers of the previous era gone, the uppermost position remains open, and into that space, sharks begin to expand, not upward in a single line, but outward in many. Their bodies, built from cartilage rather than dense bone, allow a flexibility that supports variation. Forms emerge that do not resemble the streamlined silhouettes familiar in later oceans. Some carry structures whose purpose is not immediately clear. Others develop shapes that seem to prioritize display or specialization over efficiency. The result is a collection of designs that appear provisional, as if each is testing a different approach to survival. Stethecanthus moves through these waters with a profile that defies simple interpretation. Along its back rises a flat, anvil-shaped platform, its surface covered in denticles that mirror the texture of its skin. This structure does not assist in swimming or feeding in any obvious way. It sits exposed, visible, suggesting a role tied to interaction rather than function. Some interpretations link it to mating display, a visual signal presented to others of its kind. Others consider it a form of posturing, a way to alter appearance in moments of confrontation. The exact purpose remains uncertain, preserved only in form without the behavior that once gave it meaning. Nearby, Falcatus falcatus carries a different kind of projection. In males, a spine curves forward from the head, extending over the body in a smooth arc that ends in a blade-like tip. It does not appear in females, indicating a role tied to reproduction rather than survival. The structure changes the outline of the animal, giving it a distinct silhouette that would have been visible in the water. Its presence suggests that even in a time of ecological rebuilding, selection pressures were already shaping traits beyond simple feeding and movement. Then there is Helicoprion, whose defining feature lies within the jaw itself. Instead of a row of teeth that shed and replace in sequence, it possesses a spiral whorl, a tightly coiled arrangement of hundreds of teeth that grows continuously. Each new tooth forms at the center, pushing older ones outward and downward, creating a structure that curves into itself like a rolled blade. For many years, its placement remained uncertain. Early interpretations positioned it in improbable locations, along the snout or extending outward from the body. Only with modern imaging did its true position become clear, seated within the lower jaw, integrated into the mechanism of feeding. The motion of this structure differs from a conventional bite. Rather than closing around prey in a simple arc, the spiral likely engaged in a slicing action, drawing material inward while cutting through it. Soft-bodied organisms, such as cephalopods, would have been particularly suited to this method, their forms yielding to a continuous motion rather than resisting a single force. The feeding process becomes less about crushing and more about processing, a sustained interaction rather than an instantaneous event. Despite this diversity, sharks during the Carboniferous do not yet occupy the highest level of the marine hierarchy. Many function as mid-level predators, filling specific roles within a broader system that has not yet settled into a new dominant pattern. The apex position in many environments is held by large rhizodont fish, lobe-finned forms that reach lengths of up to 7 meters. These animals inhabit freshwater systems and coastal margins, moving with a slow, deliberate strength, capable of ambush within confined spaces where their size and power can be fully applied. Across this period, the ocean and its connected waterways remain in a state of adjustment. Life continues to diversify, but the structure of dominance remains distributed, not yet concentrated in a single lineage. The variety of forms suggests a system still searching for equilibrium, where multiple strategies coexist without any one becoming definitive. Beneath this surface of variation, larger processes continue to build. Changes in climate, chemistry, and geography begin to align in ways that extend beyond individual ecosystems. The balance that allows for such diversity carries within it a growing instability, one that will not remain contained and will soon move through the entire system with a force that reshapes nearly everything it touches. There are intervals in Earth's history where change arrives so completely that the usual language of loss feels insufficient, as if the system itself has been lowered into a quieter state where almost nothing remains to move. Around 252 million years ago, the transition between the Permian and Triassic periods marks one of those intervals, a boundary defined not by a single moment, but by a compression of events that removed nearly everything at once. Within a span estimated at less than 60,000 years, approximately 96% of all marine species disappear, leaving behind a record that feels abruptly emptied. The source of this shift lies far from the ocean's surface, in a region that would one day become Siberia. There, an immense volcanic province begins to erupt, not briefly, but continuously, over roughly 1 million years. Layers of lava spread across vast distances, while gases released from deep within the Earth enter the atmosphere in sustained volumes. Carbon dioxide accumulates, raising global temperatures by 8 to 10 degrees Celsius, altering circulation patterns in both air and water. Alongside it, sulfur dioxide contributes to chemical reactions that change the composition of the atmosphere and, eventually, the oceans. As these gases dissolve into seawater, they shift its chemistry, increasing acidity and affecting the balance that marine life depends on. At the same time, warmer temperatures reduce the ocean's ability to hold dissolved oxygen. Circulation slows, stratifying the water into layers that no longer mix as freely. Oxygen becomes scarce, not in isolated pockets, but across entire regions. This condition, known as ocean anoxia, spreads through the marine environment with a uniform effect. Unlike other disruptions that affect specific groups or habitats, this process operates across all levels of the food web. Organisms that rely on oxygen for metabolism begin to fail, regardless of their size or position. Primary producers decline, reducing the flow of energy upward. Consumers at every level are affected simultaneously, not through a chain of predation, but through a shared dependence on a resource that is no longer available. The structure that supports life does not fragment gradually. It collapses as a whole. Species that had persisted through earlier extinctions reach their limit here. Trilobites, which had occupied marine environments for approximately 270 million years, disappear completely. Eurypterids, the sea scorpions that had once reached lengths of up to 2.5 meters, also vanish, leaving no continuation. Their long histories end within this interval, their forms preserved only in the layers that precede the boundary. Sharks, which had diversified during earlier periods, undergo a severe contraction. The fossil record across this boundary shows a sharp reduction in both the number of species and the abundance of individuals. Estimates suggest that as much as 90% of known shark diversity is lost. Those that remain represent a narrow subset, forms that could persist under conditions that removed most others. The aftermath does not resolve quickly. Recovery unfolds over approximately 10 million years, a duration that reflects the depth of the disruption. During this time, the ocean remains chemically unstable, its capacity to support large, complex organisms limited. The uppermost ecological position, which in earlier periods had been reoccupied within relatively short intervals, remains unfilled. It is not that a new predator fails to emerge, but that the conditions required to sustain one are absent. What continues through this interval are smaller, more adaptable lineages. Certain sharks persist, reduced in diversity but present. Early ray-finned fish remain, occupying roles that do not demand large size or high energy input. Among them are also the early ancestors of marine reptiles, still close to their terrestrial origins, not yet fully committed to life in water. These survivors share a common quality of being marginal, not dominant, existing within a system that has not yet reassembled. From these remnants, a different trajectory begins to form. The ocean that will emerge does not reconstruct the previous arrangement. It develops along a new path, shaped by the survivors and the altered conditions they inhabit. The forms that will rise from this interval will not resemble those that were lost, and the structures they create will reflect a world that has been reset at its foundation. The shoreline becomes a place of hesitation, where movement pauses between two environments that no longer feel separate. Along these margins, bodies shaped for land begin to linger in water, not as brief visitors, but as forms that return again and again, each time remaining a little longer. During the Triassic period, from 252 to 201 million years ago, this gradual leaning becomes a decisive shift, as certain reptiles begin to reverse a path taken millions of years earlier. These animals descend from tetrapods, four-limbed vertebrates that had adapted to terrestrial life over roughly 100 million years. Their skeletons, their breathing, and their methods of movement had all been shaped by air and ground. Yet, in the aftermath of the Great Collapse, the ocean presents a condition unlike anything before it, a vast system with reduced competition, open pathways, and an abundance that is no longer tightly controlled. The transition back into water does not occur once or in a single lineage. It happens repeatedly in separate groups, each finding its own way into this space. The early stages of this return retain traces of land. Limbs remain recognizable, bodies still carry the weight of terrestrial ancestry, and movement reflects a compromise between two mediums. Over time, these constraints begin to dissolve. Among the first to complete this transition are the ichthyosaurs, reptiles that move from shoreline experimentation into full marine existence with unusual speed. By the early Triassic, they have already reshaped their bodies into a form that aligns closely with open water movement. Limbs transform into fin-like structures. The tail develops a powerful propulsion system, and the body narrows into a streamlined profile that reduces resistance. Their connection to land becomes increasingly distant, not only in form but in function. Fossil evidence shows that they give birth to live young within the water, eliminating the need to return to land entirely. The pace of this transformation is notable. Within approximately 3 million years, ichthyosaurs progress from their earliest appearance in the fossil record to fully adapted marine predators. This rapid shift suggests that the environmental conditions they encountered allowed for swift expansion, with little opposition to constrain their development. The absence of established competitors creates a space where adaptation can proceed without interruption. Among these early forms, Symbospondylus youngorum emerges as a significant presence. Living around 247 million years ago, it reaches an estimated length of 17 meters, making it the largest known animal of its time, across both land and sea. Its body reflects a stage in the transition where size and aquatic efficiency begin to align. indicating that the ocean is once again capable of supporting large vertebrate life. At the same time, other reptile lineages follow different paths into the water. The nothosaurs, for example, remain connected to coastal environments. Their bodies retain longer necks and limbs that function both for swimming and for movement on land. They move through shallow waters, pursuing fish with a method that blends aquatic motion with the ability to return to shore. Their adaptation is partial, yet effective within the environments they occupy. This diversity of approaches reflects a system still forming, where multiple strategies coexist without a single dominant design. Some reptiles commit fully to the open ocean. Others remain tied to the margins, and still others explore intermediate roles. Each lineage responds to the same underlying condition, an ocean that has space available at many levels, allowing for variation rather than immediate consolidation. Within the nothosaurs, a further shift begins to take shape, one that alters the proportions of the body in a way that stands apart from previous designs. The neck extends, not as a minor adjustment, but as a defining feature, suggesting a mode of interaction with the environment that relies on reach rather than speed alone. This change does not fully emerge within the Triassic itself, but its direction is already present, carried forward by a lineage that will continue to evolve. From this lineage will come a group of marine reptiles whose structure transforms the relationship between head and body into something entirely new. Their form will not resemble the streamlined silhouettes of the ichthyosaurs, nor the partial adaptations of the nothosaurs. It will follow a different logic, one that extends the body in a direction no vertebrate had explored in this way before. The plesiosaurs. Light fades with depth, not abruptly, but through a gradual thinning where color drains away and outlines soften into shadow. In that dim gradient, where visibility narrows and pressure builds, a particular lineage moves with a precision shaped by conditions few others can endure. By the Jurassic period, ichthyosaurs have reached a form so closely aligned with the demands of open water that their bodies mirror those of fish, though their ancestry traces back to land. This resemblance is not shared origin but convergence, separate paths arriving at the same solution. Among these forms, Ophthalmosaurus eisenicus occupies a distinct space. Living between approximately 165 and 150 million years ago, it reaches around 6 meters in length, its body streamlined for sustained movement through the water column. Its most striking feature lies at the front, where each eye measures about 23 centimeters in diameter, proportionally the largest known among vertebrates. These structures are not ornamental. Their size allows for the capture of minimal available light, enabling vision in conditions where most other animals would encounter only darkness. The interior of each eye contains a ring of small bones, known as the sclerotic ring, arranged to maintain shape under pressure. At depth, where external force would distort softer structures, this ring preserves the integrity of the eye, allowing it to function without collapse. Fossil specimens retain these rings with clarity, providing direct evidence of an adaptation suited for descent into deeper layers of the ocean. This capacity extends the reach of Ophthalmosaurus into regions that remain inaccessible to many predators. In these depths, movement becomes quieter, and encounters occur within limited visual range. The ability to detect faint contrasts offers an advantage, allowing it to navigate and feed within a zone that lies between the illuminated surface and the complete absence of light below. Reproduction within this lineage reflects a complete commitment to marine life. Fossil evidence shows individuals preserved with developing young inside the body cavity, including a specimen where a juvenile is positioned tail first during birth. This orientation reduces the risk of drowning at the moment of emergence, indicating a process adapted specifically to the surrounding medium. The absence of any requirement to return to land marks a full transition from terrestrial ancestry to an entirely aquatic existence. Further insight comes from the composition of their tissues. Isotope analysis of bone collagen suggests that some ichthyosaurs maintained body temperatures above that of the surrounding water. This capacity would support sustained activity across a range of conditions, enabling them to move between depths and latitudes without the limitations faced by organisms whose internal temperature mirrors their environment. The exact mechanism remains under study, but the evidence points toward a level of physiological regulation that extends beyond what is typically associated with reptiles of their time. Surface appearance also reveals a pattern consistent with open water living. Analysis of preserved pigment structures indicates a distribution of coloration known as countershading, where the upper body is darker and the underside lighter. This arrangement reduces visibility from both above and below, blending the animal into the surrounding light gradient. It is a strategy seen in modern marine predators, suggesting a similar mode of interaction with prey and environment. Despite these adaptations, ichthyosaurs do not occupy the highest position within the Jurassic marine hierarchy. Their speed, sensory capacity, and physiological traits place them within a role focused on pursuit and capture in open water. But the apex position is held by other forms that operate with different strategies and structures. Over time, the presence of ichthyosaurs begins to diminish. By approximately 90 million years ago, they disappear from the fossil record, their decline occurring well before the larger extinction event that will later reshape the planet. The reasons for their disappearance are still being examined, with multiple factors considered, including environmental shifts and changes in competition. Their absence does not leave the ocean empty. Other lineages persist, continuing to move through the water with forms that diverge from the streamlined efficiency of the ichthyosaurs, carrying forward different solutions to the same enduring conditions. Power in this era gathers at the front of the body, concentrated into mass and leverage, rather than extended through length or speed alone. Among the descendants of the earlier long-necked forms, a branch emerges that reverses that proportion, shortening the neck, enlarging the head, and turning the body into a platform for force. These are the pliosaurs, marine reptiles with four flippers that move not with continuous grace, but with controlled bursts, each motion aligned with the act of capture. Their proportions shift the balance of the entire body. The head becomes dominant, the neck reduced to a compact connection that supports a skull of unusual size. The limbs, shaped into broad flippers, generate propulsion through coordinated strokes that allow sudden acceleration rather than sustained cruising. The result is an animal built for approach and impact, capable of closing distance quickly and delivering force at the moment of contact. Kronosaurus queenslandicus, living during the early Cretaceous between approximately 125 and 99 million years ago, reflects this design at a large scale. Its total length reaches around 9 to 10 meters, but the most striking measurement lies in the skull, extending to roughly 2.7 meters. This dimension alone exceeds the full body length of many modern marine predators, placing the feeding apparatus at a scale that defines the animal's presence. Another form, Pliosaurus funki, discovered in Svalbard and formally described in 2012, extends this pattern further. Estimated between 10 and 13 meters in length, it carries a skull of approximately 2 meters, equipped with multiple rows of conical teeth that interlock when the jaws close. Each tooth can reach up to 30 centimeters, arranged not for slicing, but for penetrating and holding, creating a grip that resists escape once contact is made. The force generated by this structure has been estimated at around 33,000 newtons, derived from analysis of fossil material and the inferred attachment of muscles. This level of pressure exceeds that calculated for any other known marine animal. When expressed through the arrangement of teeth and bone, it allows the animal to pierce and crush with a directness that leaves little margin for resistance. Movement supports this capability. The four flippers, positioned along the body, function in coordinated pairs, producing bursts of speed that bring the animal into range. This mode of locomotion resembles the acceleration patterns seen in modern marine mammals, where energy is applied in short intervals to close distance rapidly. The body is not optimized for endurance across long distances, but for decisive engagement within a defined space. Evidence of feeding behavior appears in the remains left behind. Fossil sites associated with pliosaurs contain bones marked by tooth impressions that match their dentition, including those of ichthyosaurs, large fish, and other plesiosaurs. These markings indicate a role at the top of a complex system where even other large predators form part of the available prey. The interactions are not limited by size alone, but by opportunity and position within the water column. Sensory structures support this role. Enlarged regions of the skull associated with smell suggest a capacity to detect chemical traces across distance, while the presence of a lateral line system allows the detection of movement through changes in water pressure. These combined inputs provide a means of locating prey beyond immediate visual range, guiding the animal toward activity that might otherwise remain undetected. For over 80 million years, pliosaurs maintain this position across the Jurassic and into the early Cretaceous. Their design remains consistent, refined within its parameters, rather than replaced by entirely new forms. The ocean during this time supports multiple large predators, yet the pliosaurs occupy a distinct level, defined by the concentration of force and the ability to apply it with precision. Over time, however, their presence begins to diminish. The conditions that sustained them shift, altering the balance that once favored their design. Their disappearance does not occur in isolation, but within a broader transition that affects multiple lineages. In their absence, another group expands into the space they leave behind, carrying a different structure and a different approach to dominance within the same environment. Balance in this interval does not settle into a single peak, but spreads across several forms that share the same space without merging into one hierarchy. During the Jurassic period, from 201 to 145 million years ago, the ocean holds multiple predators at comparable scale, each shaped by a different ancestry, each operating within a distinct pattern of movement and capture. The result is not a single dominant lineage, but a layered system where several occupy positions that approach the top at the same time. Within this arrangement, pliosaurs remain the most direct expression of concentrated force. Their compact proportions and enlarged skulls allow them to function as ambush predators in mid-water, closing distance through sudden acceleration and delivering impact at close range. Their presence defines one axis of predation, where encounters are brief and decisive, shaped by timing and proximity rather than extended pursuit. Alongside them move the ichthyosaurs, carrying a different approach. Their bodies, refined through convergence, allow sustained speed across open water. They operate within a wider range, diving and ascending through the water column, pursuing prey over distance rather than relying on concealment. Their capacity to regulate internal conditions and their visual adaptations extend their reach into regions that other predators enter less frequently. A third lineage introduces yet another form into this shared environment. Marine crocodilians, known as metriorhynchids, undergo a transformation that removes their connection to land entirely. Limbs become reduced and reshaped, the tail develops into a structure capable of propulsion, and the body takes on a streamlined outline suited for continuous swimming. Among them, Dacosaurus maximus carries a skull whose proportions and dentition differ from the conical gripping teeth associated with most crocodilians. Its teeth are serrated, arranged for cutting rather than holding, aligning its feeding behavior more closely with that of terrestrial predators than with its aquatic relatives. Below these reptiles, sharks remain present, though not at the highest level. Hybodont sharks, reaching lengths of 2 to 3 meters, occupy roles within the secondary tier, interacting with prey that lies beneath the reach of larger predators. Their forms are robust, capable within their range, yet they do not dominate the system in the way reptiles do during this period. The coexistence of these lineages creates a structure that is unusually complex. Crocodilians, plesiosaurs, ichthyosaurs, and sharks move within the same vertical space, each following its own pattern, occasionally intersecting in ways that lead to direct interaction. Predation does not follow a simple chain but forms a network where one predator may become prey under certain conditions, and boundaries between roles remain fluid. Supporting this system is a base of life that provides both abundance and diversity. Ammonites, with their coiled shells and varied forms, populate the water in large numbers, forming a substantial component of the available biomass. Schools of fish move through these environments, their movements creating shifting patterns that attract predators from multiple directions. At the same time, early representatives of modern teleost fish begin to appear, introducing a lineage that will eventually become the most species-rich group of vertebrates. The interaction between these elements produces a dynamic balance where energy flows through multiple pathways rather than a single dominant channel. Each predator influences the behavior of those beneath it, while also adapting to the presence of others at similar levels. The system maintains itself not through simplicity, but through the coexistence of varied strategies that do not fully overlap. This arrangement persists for millions of years, sustained by environmental conditions that support both the predators and the prey they depend on. Yet, as in earlier periods, these conditions are not fixed. Changes begin to accumulate, altering temperature, sea level, and the distribution of habitats across the planet. The structure that allows for such complexity depends on these underlying factors, and as they shift, the balance begins to adjust. The transition into the next period carries these changes forward. The Cretaceous emerges, with seas extending across large portions of the continents, warmer and more expansive, creating new environments that reshape the possibilities within the ocean and open space for another lineage to rise within this evolving system. Water advances across land in a way that leaves no sharp boundary behind, spreading into low regions, filling basins, and linking distant coastlines into a continuous network of shallow seas. During the Cretaceous period, from 145 to 66 million years ago, this expansion reaches a scale unmatched in the previous 500 million years. Beneath the surface, the ocean floor is actively reshaped by volcanic activity along mid-ocean ridges, where new crust forms and displaces older sections outward. This expansion lifts the ocean basins, causing water to rise and spill across continental interiors. At its peak, This process covers roughly 40% of the present-day continents with shallow marine environments. A broad seaway divides North America from north to south, connecting polar waters to tropical regions in a continuous passage. Similar expanses extend across northern Europe and Central Africa, forming inland seas that transform previously terrestrial landscapes into marine habitats. These waters are not deep, but wide and interconnected, creating extensive shelf regions where light penetrates easily and nutrients circulate efficiently. The consequence of this geography is an increase in biological productivity. Shallow seas provide ideal conditions for the growth of microscopic life, which forms the base of the food web. As these organisms multiply, they support larger populations of invertebrates and fish, which in turn sustain higher levels of predation. The expansion of habitat leads to an expansion of energy flow, allowing ecosystems to support greater numbers and sizes of animals. Temperature plays a significant role in shaping this environment. Global conditions during the Cretaceous are warmer than those of later periods, with no permanent ice at the poles and elevated temperatures across all latitudes. Equatorial sea surface temperatures may reach between 35 and 37 degrees Celsius, while polar waters remain above freezing throughout the year. This uniform warmth reduces temperature gradients, allowing marine organisms to occupy regions that would otherwise be restricted by colder conditions. The ocean that forms under these circumstances becomes highly connected, both physically and biologically. Currents move more freely between regions, distributing nutrients and organisms across vast distances. This connectivity supports a system where large predators can move through extensive ranges, encountering prey across multiple habitats without encountering the barriers that would later emerge as climates cool and sea levels fall. Within this environment, the conditions favor the development of large marine predators. The combination of abundant prey, stable temperatures, and expansive habitats allows for sustained growth and reproduction at scales that had not been supported since earlier periods. The ocean becomes capable of maintaining multiple large species simultaneously, each occupying a role within a complex and productive system. During the early part of this period, some of the previously dominant lineages remain present, though their influence is beginning to decline. Pliosaurs continue to exist but show signs of reduction in diversity and abundance. Ichthyosaurs persist as well, though their numbers decrease as the period progresses, leading toward their eventual disappearance. Their roles within the ecosystem begin to shift, creating space for other forms to expand. Into this changing environment, a different lineage begins to extend its reach. Originating from small, semi-aquatic ancestors that had remained close to coastal margins for millions of years, these reptiles begin to move further into open water. Their early forms retain features suited to both land and shallow environments, but over time, their bodies undergo rapid transformation, aligning more closely with the demands of a fully marine existence. This transition occurs at a pace that stands out within the broader history of vertebrate evolution. Within a relatively short geological interval, these animals shift from limited aquatic activity to complete integration within marine systems. Limbs become adapted for swimming, tails develop structures suited for propulsion, and the body elongates in a way that supports movement through open water. The lineage responsible for this transformation traces back to monitor lizards, terrestrial reptiles whose descendants include the modern Komodo dragon. Their ancestry carries forward into a form that diverges significantly from its origin, shaped by the conditions of the Cretaceous ocean and the opportunities it presents. The shape that enters the water at first seems unremarkable, a long-bodied reptile moving between shore and sea. carrying the proportions of land with only partial adaptation to its new environment. Around 100 million years ago, these early mosasaurs measure between 1 and 2 meters in length, inhabiting coastal shallows where fish move in dense, accessible groups. Their limbs still retain a degree of structure suited for land, their motion a blend of paddling and undulation, closer in appearance to large marine iguanas than to the fully developed predators they will become. Their origin lies within the varanid lineage, placing them alongside monitor lizards and, more distantly, within the broader group that includes snakes. This ancestry shapes their initial form, providing a flexible body and a feeding system already capable of handling active prey. As they spend more time in water, these inherited traits begin to shift, guided by the demands of a medium that rewards different movements and structures. Over the next 30 million years, the transformation proceeds with unusual speed. Bodies elongate further, limbs reshape into paddle-like structures that provide stability and control, and the tail develops into a primary source of propulsion. Movement becomes defined by lateral undulation, a side-to-side motion that translates efficiently into forward thrust. This mode differs from the limb-driven propulsion of other marine reptiles, aligning more closely with the mechanics of crocodilian swimming, yet extended into open ocean conditions where sustained movement is required. As their bodies adapt, their size increases in parallel. Tylosaurus proriger reaches lengths of 12 to 14 meters, its form streamlined for movement across large distances. Hanosaurus bernardi extends even further, potentially approaching 15 meters, while Mosasaurus hoffmanni develops a more robust structure, combining length with a heavier build that emphasizes strength. These variations reflect different approaches within the same lineage, each suited to particular roles within the expanding marine system. The most distinctive feature of these animals lies in the structure of the jaw. Unlike earlier predators, whose jaws close along a fixed hinge, mosasaurs possess a flexible joint within the lower jaw that allows it to expand outward. This intramandibular joint enables the mouth to open beyond the limits imposed by a rigid structure, accommodating prey larger than would otherwise be possible. Inside the mouth, a second set of teeth lines the palate, positioned to grip prey as it is drawn inward. The interaction between these elements creates a feeding mechanism that operates in stages. Outer teeth secure the prey, while the inner teeth prevent retreat, guiding it deeper into the mouth. The flexibility of the jaw allows the entire structure to adjust around the shape of what is being consumed, reducing the chance of escape once contact is made. This arrangement does not rely on a single decisive bite, but on a sequence of movements that draw the prey inward until it is fully contained. The significance of mosasaurs was recognized early in the study of prehistoric life. In 1764, a fossil discovered in a limestone quarry in Maastricht, Netherlands, provided one of the first clear examples of a large, extinct marine reptile. The specimen, later identified as Mosasaurus hoffmannii, predates the formal naming of dinosaurs by several decades, placing these animals among the earliest subjects of scientific investigation into ancient life. Their reproduction confirms a complete transition to marine existence. Fossil evidence indicates that mosasaurs gave birth to live young in open water, eliminating any dependence on land for reproduction. This adaptation allows them to occupy the ocean continuously, from birth through adulthood, without returning to terrestrial environments. By approximately 80 million years ago, mosasaurs have expanded across all major oceans, replacing earlier dominant predators and establishing themselves at the highest level of the marine hierarchy. Their distribution is global, their presence consistent, and their scale unmatched within their time. The ocean that supports them has reached a condition where a single lineage can occupy the apex position across multiple regions simultaneously, maintaining that role without immediate challenge. What remains inside a body can persist long after the body itself is gone, sealed within stone as a quiet record of behavior that no longer occurs. In a specimen of Tylosaurus recovered from the Pierre Shale of Kansas, the interior preserves a sequence of meals taken at different moments, layered within the same individual. Among the remains are bones from a flightless diving bird, fragments of a large bony fish, and the partial skeleton of a smaller mosasaur. These are not variations of a single prey type, but distinct organisms from separate branches of life, gathered within one predator, indicating a feeding pattern that extends across multiple levels of the ecosystem. Elsewhere, the evidence appears not inside the predator, but on the bodies of other large marine animals. Fossilized bones of plesiosaurs bear marks that correspond in spacing and curvature to mosasaur teeth. These impressions occur on skulls and paddle elements, areas that would have been targeted during active encounters. The presence of such markings confirms that mosasaurs engaged with animals of comparable size, not only scavenging but initiating contact in ways that left lasting traces on bone. Within the same environments, variations in tooth structure reveal a division of roles among mosasaurs themselves. Globidens alabamensis carries rounded, blunt teeth shaped for crushing rather than piercing. These surfaces align with the processing of hard-shelled organisms such as ammonites and bivalves, which require force distributed across a broader area rather than concentrated at a point. In contrast, other mosasaurs in the same waters possess sharper, conical teeth suited for gripping soft-bodied prey. The coexistence of these forms indicates a system where different feeding strategies operate simultaneously, reducing overlap and allowing multiple species to occupy adjacent positions. A more recent discovery extends this range further. Xenodon's kalmanchari, described in 2020, presents a dentition unlike any previously known within the group. Its teeth are arranged in interlocking rows with blade-like edges, forming a structure that functions in cutting rather than gripping or crushing. This configuration resembles that of certain sharks, yet arises independently within a reptilian lineage. The presence of such a design suggests that mosasaurs explored a wider set of feeding methods than earlier evidence had indicated, adapting their jaws to process prey in different ways depending on ecological opportunity. Movement supports these feeding strategies. Analysis of tail structure and muscle attachment points suggests that mosasaurs could generate short bursts of speed between 4 and 6 meters per second. This velocity, sustained within water by an animal of considerable size, allows rapid approach and engagement. The combination of speed and jaw flexibility creates a system where prey can be overtaken and secured within a brief interval. Their sensory configuration aligns with this pattern. The nostrils, positioned high on the skull above the level of the eyes, allow the animal to approach the surface with minimal exposure, taking in air before returning below. This arrangement reduces the time spent at the interface between air and water, maintaining continuity of movement. The eyes themselves, supported by preserved sclerotic rings, indicate a capacity for function in low light conditions, extending activity into depths or times of day where visibility is limited. Taken together, these elements form a detailed picture of a lineage that has diversified across multiple roles. By the late Cretaceous, mosasaurs are not confined to a single mode of predation. Some operate within reef environments, processing hard-shelled organisms with specialized dentition. Others pursue prey across open water, relying on speed and coordination. Still others engage with large animals, applying force through jaws designed to secure and contain. This range of strategies allows a single lineage to occupy positions that, in earlier periods, had been distributed among several groups. The ecological space, once divided between different marine reptiles, becomes concentrated within mosasaurs, each form adapting to a particular niche while remaining part of a broader system that shares a common origin. Abundance in the ocean is rarely visible as a single form, but as a layering of life that fills the water at every level, each part supporting the next in a quiet transfer of energy. During the Cretaceous, this layering reaches a density that allows the largest predators to exist, not as isolated individuals, but as a sustained presence across entire seas. Beneath them lies a foundation unlike any that came before, a vast and continuous supply of prey that shapes the scale of everything above it. Among the most prominent elements of this foundation are the ammonites, coiled cephalopods whose shells trace a spiral that expands outward with each stage of growth. Related to the nautilus, they occupy a wide range of forms and sizes, with over 10,000 species identified across a lineage that extends for 330 million years. Their diversity reflects an ability to adapt to multiple environments, from near-surface waters to deeper zones where light begins to fade. Their shells are not solid masses, but divided internally into a series of chambers connected by a central tube. By adjusting the balance of gas and fluid within these chambers, ammonites maintain control over their position in the water. This buoyancy system allows them to move vertically with precision, rising or descending without constant expenditure of energy. Through this mechanism, they inhabit a range of depths, distributing themselves across the water column in patterns that vary with conditions. Size within this group spans several orders of magnitude. Many species remain small, measuring only a few centimeters across, while others reach dimensions that alter their presence entirely. Parapuzotia sepenredensis, from the late Cretaceous, develops a shell with a diameter of 2.55 meters, extending wider than a dining table. Such individuals move slowly, their mass supported by internal structure, contributing to a population that includes both small, numerous forms and large, infrequent ones. In regions where conditions favor productivity, ammonites occur in densities that exceed what is observed in modern oceans. Their shells, varying in size and orientation, drift through the water in large numbers, creating a visual field composed of repeated spirals. Movement within such an environment involves passing through layers of these forms, each occupying its own depth, yet connected through the same system of growth and reproduction. Alongside them, another group of cephalopods provides a different type of resource. Belemnites, with their elongated bodies and internal calcite structures, move more actively through the water, forming a faster, more mobile component of the prey base. Their bodies offer a concentrated source of nutrition, supporting predators that operate within intermediate levels of the system. These animals sustain a network of interactions that extends upward, linking smaller predators to those above them. At the same time, fish populations expand significantly. Teleost fish, the group that will later dominate modern marine environments, diversify rapidly during this period. Their forms vary widely, occupying different ecological roles and adding another layer to the available prey. Schools of these fish move through the water in coordinated patterns, their collective motion creating shifting targets for predators that rely on speed and timing. The combined presence of ammonites, belemnites, and teleost fish produces a system with a high and continuous flow of energy. This abundance supports not only individual predators, but entire populations of large animals. The scaling of mosasaurs, reaching lengths of 12 to 15 meters, becomes possible within this context. The ocean provides enough resources to sustain these sizes at densities that would otherwise be unattainable. Such a system depends on stability across multiple levels, the productivity of microscopic organisms, the distribution of nutrients, and the circulation of water all contribute to maintaining this balance. When these underlying conditions persist, the structure above them remains intact, supporting a wide range of life forms in a coordinated system. If the base of this structure is removed, the effects extend upward with little delay. The layers that depend on it cannot sustain themselves independently, and the entire system begins to contract. In the Cretaceous, this foundation remains in place for millions of years, allowing the largest predators to thrive. Yet the continuity of this abundance is tied to conditions that will not remain unchanged. A thin line in the rock marks the transition, a boundary so narrow it can be traced across continents and oceans alike, separating what came before from what followed. At 66.043 million years ago, that line corresponds to a moment when a body from space intersected with the Earth, altering the conditions of the planet with a speed that contrasts sharply with the gradual changes that usually define geological time. The object, now known as the Chicxulub impactor, measured between 10 and 15 kilometers in diameter. It struck the shallow carbonate platform of what is now the Yucatan Peninsula in Mexico, traveling at approximately 20 kilometers per second. The energy released at impact has been estimated at around 100 teratons of TNT, equivalent to roughly 10 billion times the atomic bomb dropped on Hiroshima. This release of energy did not disperse evenly, but concentrated at the point of contact, generating effects that extended outward in expanding waves. Within a radius of about 1,500 kilometers, the immediate consequences were overwhelming. A thermal pulse moved across the surface, raising temperatures to levels that ignited organic material and altered landscapes within minutes. At the same time, the displacement of water generated a megatsunami, with initial wave heights reaching hundreds of meters, propagating outward across the Gulf of Mexico and into the Atlantic basin. These waves carried energy across large distances, interacting with coastlines and reshaping shallow marine environments. Beyond this immediate zone, the impact produced a different set of effects that unfolded over a longer interval. The collision vaporized large quantities of sulfur-rich rock, injecting sulfur aerosols and fine particulate matter into the upper atmosphere. These materials spread globally, forming a layer that reduced the amount of sunlight reaching the surface. Within weeks, light levels declined significantly, altering the balance that supported photosynthetic life. Phytoplankton, which form the base of the marine food web, depend on sunlight to carry out the processes that sustain their populations. As light diminished, their numbers declined rapidly. Within months, large portions of this primary production ceased, removing the foundation upon which higher levels of the system depended. Without phytoplankton, zooplankton populations decreased, followed by small fish that relied on them for food. This sequence continued upward through the trophic structure. Medium-sized predators lost their food sources, and in turn, the largest predators found themselves without sufficient energy input to sustain their populations. The collapse did not proceed through direct competition or selective pressure among species, but through the removal of the base that supported all of them. Each level depended on the one below, and as those lower levels diminished, the structure above them could not remain intact. The result was a near-complete restructuring of marine life. Mosasaurs disappeared entirely, with no species persisting beyond this boundary. Plesiosaurs followed the same path, their long lineage ending at the same interval. Ammonites, which had existed for approximately 330 million years, also vanished, leaving no direct descendants in the global ocean. Their absence removed a major component of the prey base that had supported earlier ecosystems. A small number of groups persisted through this transition. Certain sharks, bony fish, sea turtles, and early marine mammals survived, generally limited to sizes below about 2 meters. Their continued existence reflects a capacity to function within reduced food availability and altered environmental conditions. These survivors represent lineages that could endure the constraints imposed by the new state of the ocean. In the aftermath, the marine environment differs significantly from its previous form. Reduced light, lower temperatures, increased acidity, and diminished oxygen levels create conditions that limit the diversity and abundance of life. The system does not return immediately to its prior complexity, but enters a phase where rebuilding must occur from a much smaller base. The change at this boundary is more complete than any since earlier major extinctions, resetting the structure of the ocean in a way that removes dominant lineages and alters the pathways through which energy moves. What follows emerges not as a continuation, but as a new configuration shaped by the conditions left behind. Sediment settles differently in the layers that follow, finer, more uniform, as if the ocean itself has relaxed after the violence recorded beneath it. In these Paleocene waters, spanning 66 to 56 million years ago, there is a quiet absence that shapes everything that moves through it, an absence not of life, but of dominance. The uppermost position in the marine hierarchy remains unclaimed, not weakened or contested, but simply empty. For roughly 10 million years, no large apex predator occupies this space. The distinction is precise. An apex predator is an animal that, at adult size, has no natural predators and exerts top-down influence across its ecosystem. During this interval, that role does not exist in any meaningful form. Energy continues to move through the system. Prey species recover, populations expand, yet nothing rises high enough to impose the kind of control once exercised by the great marine reptiles. The survivors that persisted through the boundary carry on in reduced forms. Sharks remain present, but their size reflects the constraints of the environment they endured. The largest Paleocene species reach perhaps 3 to 4 meters, capable hunters within their scale, but far removed from the dimensions and ecological reach of the mosasaurs that preceded them. Their bodies trace familiar outlines, efficient and enduring, yet they move within a system that has not yet rebuilt the conditions required for larger forms. Sea turtles and large bony fish occupy the upper tiers in this reshaped ocean. Some grow to considerable size, navigating coastal shelves and open waters with steady persistence. They hunt, they migrate, they reproduce, filling ecological roles left vacant, but their influence remains localized. They do not restructure entire communities or alter the distribution of life across vast regions. The cascading effects associated with a true apex presence remain absent, leaving the system comparatively open, less tightly regulated, more evenly distributed. Above and around them, the lower levels of the food web continue their gradual return. Phytoplankton populations recover as light stabilizes, restoring the primary productivity that supports everything above. Zooplankton follow, then small fish, each layer rebuilding in sequence, re-establishing the pathways through which energy flows. The ocean clears, chemically and visually, and with that clarity comes opportunity, though it remains unrealized for an extended interval. On land, mammals diversify rapidly in landscapes no longer dominated by large reptiles. They explore niches, expand in size and form, testing possibilities across forests and plains. In the ocean, however, their presence remains peripheral. The transition from land to sea has not yet unfolded in any substantial way. The shoreline marks a boundary that few have crossed with commitment, leaving the marine realm still largely defined by lineages that endured the extinction. This 1-0 million year interval stands as one of the most revealing passages in marine evolutionary history. The apex predator position, once repeatedly filled and vacated across earlier eras, remains structurally available. The prey base rebuilds beneath it, the environmental conditions stabilize, yet no lineage has yet assembled the combination of traits required to occupy it. The system waits, not passively, but as a set of conditions aligning toward a threshold not yet reached. Within this waiting, subtle movements begin. Among sharks, a lineage known as the Otodontids increases in size across generations, each increment small, cumulative, almost imperceptible within a single lifetime. Their teeth, preserved in the record, hint at a trajectory that extends beyond the scale of their Paleocene ancestors. At the edges of rivers in what is now Pakistan, a small hoofed mammal spends more time in the water, its limbs adjusting, its body redistributing weight and buoyancy in ways that suggest a gradual departure from land. These developments unfold quietly, without immediate consequence, separated by habitat and form, yet linked by the same opening in the system above them. One lineage refines predation within the water, the other begins to re-enter it from land, each moving toward a future in which their paths will intersect. As the Paleocene gives way to the Eocene, the conditions that have been accumulating begin to express themselves more visibly, and the long interval of waiting approaches its end through transformation rather than interruption. In the layered record of stone, certain sequences read almost like a continuous motion, as if the boundary between land and sea had been crossed not in a single step, but through a steady, deliberate descent. Around 53 million years ago, in what is now Pakistan, a small mammal moves along the margins of rivers and coastal flats. Its body is built for land, four-legged, compact, with hooves touching sediment that shifts between dry ground and shallow water. This animal is known as Pakicetus ataki. Pakicetus stands at the beginning of a transformation that will alter the structure of the ocean. It resembles a dog or a wolf in general form, yet its lineage lies elsewhere. It belongs to the rowlead artiodactyls, even-toed hoofed mammals, more closely related to modern hippopotamuses than to any carnivore. Its skull is elongated, its eyes set high, positioned in a way that suggests awareness of the waterline. The bones of its limbs are unusually dense, reducing buoyancy, allowing it to remain stable while waiting. Within its skull, a more decisive feature is preserved. The inner ear shows a thickened structure found only in cetaceans, establishing a direct and unambiguous link to whales, dolphins, and porpoises. From this point, the transition unfolds with uncommon clarity. Over approximately 15 million years, a sequence of forms appears in the fossil record, each one carrying forward the structure of the last, while introducing changes that shift the animal further into the water. Ambulocetus natans, emerging around 49 million years ago, grows larger, its limbs shortening relative to its body, its movement in water driven by spinal undulation, similar to modern otters. It is capable, both on land and in water, though already its center of activity has begun to shift. By 47 million years ago, Rhodocedus casranii presents a more advanced stage. Its hind limbs are reduced, no longer suited for extended movement on land. The tail lengthens, becoming a primary driver of propulsion. The nasal openings begin a slow migration along the skull, moving away from the tip toward the top, a subtle repositioning that will eventually become the blowhole. The body elongates. The spine flexes with increasing efficiency in water, and the connection to land weakens further. In Dorodon atrox, dating from 40 to 36 million years ago, the transition reaches completion. The body is fully streamlined, the hind limbs reduced to small vestigial structures that no longer contribute to movement. Locomotion is entirely aquatic, driven by the tail. Fossil evidence shows individuals preserved with developing young inside the body, indicating birth in open water. The shoreline is no longer required. The animal lives and reproduces entirely within the ocean. Alongside Dorodon, another form appears, extending the trajectory into a new scale. Basilosaurus isis, living between approximately 40 and 34 million years ago, reaches lengths of 15 to 20 meters. Its body is long and sinuous, almost eel-like in proportion, moving through the water with continuous undulation. The skull carries two distinct types of teeth, those at the front adapted for gripping, those at the rear bearing serrated edges suited for shearing flesh. This arrangement allows it to seize, hold, and process large prey with efficiency. Evidence preserved in fossilized bone reveals behavior that places Basilosaurus at the top of its environment. Bite marks matching its dentition appear on the skulls of juvenile Dorodon, indicating predation on closely related species. The pattern is consistent with an animal exerting control across multiple levels of its ecosystem, capable of targeting both smaller prey and animals of comparable lineage. Within the span of these 15 million years, a lineage that began as a wading hoofed mammal produces a fully marine predator of immense size and capability. The transition is not a sudden leap, but a continuous sequence, each form carrying the imprint of the last, each adjustment building toward a body entirely shaped by water. The result is a new kind of apex presence, one that arises not from the long continuity of marine lineages, but from a return, reshaped, refined, and fully committed to the ocean that had remained open. Fragments of bone emerge from coastal desert rock in Peru, lifted from layers that once lay beneath a warm Miocene sea. Among them, a skull begins to take shape, massive and unfamiliar in proportion, its surfaces carrying the imprint of an animal built for force rather than subtlety. The site, the Pisco Formation, preserves an ocean long vanished, and within it, around 12 to 13 million years ago, this skull belonged to a predator unlike any living whale. The animal is named Leviathan melville, a deliberate echo of older stories carried into scientific language. Yet its reality rests in measurable structure. The skull alone extends several meters, with jaws that close along a line reinforced for impact. From these jaws project teeth of extraordinary size, reaching approximately 36 centimeters in length, rooted deeply in both the upper and lower jaws. Unlike modern sperm whales, which carry functional teeth only below and rely on suction to draw in soft-bodied prey, this animal bears a full set of interlocking weapons designed for seizing and cutting large, resisting bodies. Estimates place its total length between 13.5 and 17.5 meters, with mass approaching the upper range calculated for Megalodon. In this interval of the Miocene, such dimensions position it among the largest active predators present in the ocean. Its proportions suggest a powerful anterior, with musculature concentrated around the skull and neck, supporting rapid closure of the jaws and control of prey during struggle. The eye sockets indicate forward placement, allowing a degree of binocular overlap, a trait associated with depth perception in active hunters that track moving targets in open water. The ocean it inhabits has already recovered into a system capable of supporting large bodies. Baleen whales are diversifying, filtering immense volumes of plankton and converting that productivity into mass. Seals and other marine mammals occupy coastal and pelagic zones, adding layers to the food web. Within this environment, Leviathan does not specialize in small or soft prey. Its dentition and skull mechanics indicate an animal adapted to pursue and subdue other large vertebrates, including whales of moderate size, using direct force rather than suction. In the same waters, another lineage has reached comparable scale. The otodontid sharks have continued their gradual increase in size, culminating in forms attributed to Megalodon. These sharks move through the same warm Miocene seas, overlapping in both geography and prey preference. Both lineages focus on large marine mammals. Both operate within similar thermal and ecological ranges, and both possess the capacity to influence the structure of the communities around them. How these two predators interact remains unresolved. The fossil record preserves teeth, bones, and occasional traces of feeding, but direct encounters are not recorded with clarity. It is possible that they occupied slightly different depths or hunting times, reducing direct conflict. It is equally possible that their paths crossed more directly, with competition expressed through pressure on shared prey populations or through encounters that left little lasting trace. The absence of definitive evidence leaves the relationship open, defined by proximity and potential rather than documented interaction. Around 9 to 8 million years ago, Leviathan disappears from the record. The cause is not clearly established. Changes in ocean circulation, shifts in prey distribution, or broader climatic adjustments may have altered the balance that supported such large predatory mammals. What remains is the pattern, a lineage rising to occupy the highest level of the marine system, then receding as conditions shift beyond its range of adaptation. With its disappearance, the uppermost position becomes less contested. Megalodon persists beyond this point, continuing within an ocean that still supports large prey, but no longer contains a mammalian predator of equivalent size and capability. The space at the extreme apex narrows to a single dominant occupant, shaped by the same forces that have repeatedly filled and cleared it across earlier ages, now entering another phase defined by absence and continuation intertwined. A pattern has been forming across these layers, a recurring emergence at the uppermost limit of the ocean, followed by an eventual absence. Within that pattern, one name appears late, fully realized, carrying forward the accumulated innovations of everything that came before. Otodus megalodon enters the record around 23 million years ago and remains present until approximately 3.6 million years ago, spanning 19.4 million years as one of the defining apex predators of its time. Its scale is reconstructed from teeth, vertebral fragments, and comparative anatomy with living sharks. Estimated length ranges between 15 and 20 meters, with body mass between 50 and 100 tons. These values are not fixed but bounded by models that reflect genuine uncertainty in how cartilage-based skeletons translate into full body proportions. What remains consistent across all reconstructions is magnitude, an animal operating at a size that places it among the largest predatory vertebrates to have ever lived. The teeth provide the clearest evidence of its design. Individual crowns reach up to 18 centimeters, triangular in shape, with finely serrated edges. They are built for cutting rather than crushing, passing through flesh with minimal resistance, then being replaced continuously throughout life. Like all sharks, Megalodon sheds and regenerates teeth in a steady cycle, maintaining a functional cutting edge at all times. These teeth are distributed globally in the fossil record, found across continents, marking a predator that ranged through much of the world's oceans. Bite force estimates vary from 6,000 to 18,000 newtons, sufficient to process large prey efficiently, though not exceeding the highest forces calculated for earlier marine predators. The effectiveness of the bite lies not only in force, but in the geometry of the teeth and the mechanics of the jaw, allowing repeated, controlled slicing actions that reduce large bodies into manageable sections. Chemical signatures preserved in fossil teeth provide further insight. Nitrogen isotope analysis, conducted in 2022, places Megalodon at a hyperapex trophic level, meaning it consumed animals that were themselves apex predators. This position sits above that of any modern marine animal, indicating a level of ecological dominance that extends beyond simple predation on herbivores or mid-level carnivores. It occupied the highest tier available in its environment, shaping the distribution and behavior of species beneath it. The primary prey base consists of large baleen whales. Fossil whale bones bearing characteristic bite marks, along with embedded Megalodon teeth, have been recovered from multiple regions. Some of these bones show signs of healing, indicating individuals that survived initial attacks. The interaction between predator and prey unfolds not as a single decisive event, but as repeated encounters across the lifespan of both, influencing migration patterns, group behavior, and the development of defensive strategies. Evidence of reproduction appears in localized concentrations of smaller teeth within warm, shallow marine deposits. These sites are interpreted as nursery areas, where juvenile Megalodon, measuring around 2 meters at birth, develop within relatively protected environments before moving into open water. Growth toward adult size is gradual, extending over years, requiring a stable and abundant food supply throughout development. Thermal biology offers another layer of refinement. Isotope data suggests that Megalodon maintained body temperatures above the surrounding water, a condition similar to regional endothermy observed in modern laminid sharks such as the shortfin mako. This capability would have expanded its usable range, allowing movement into cooler waters while maintaining high levels of activity, increasing its access to prey across different environments. Within the context established across earlier ages, Megalodon stands as both culmination and continuation. Its size, feeding strategy, and physiological adaptations represent a convergence of traits that have appeared in different forms across previous apex predators. It is distinct in its combination, yet consistent in its role. The ocean supports it for millions of years, providing the energy required to sustain such a large and active organism. And yet, as with those that came before, its presence is bounded. The record shows its arrival, its expansion, and eventually its absence, a familiar sequence repeating at the highest level of the marine system, where even the most dominant forms remain subject to the broader changes that shape the ocean itself. A shift begins not in the animals themselves, but in the background conditions that have supported them for millions of years. Around 3.6 million years ago, the Earth enters a phase of cooling that leaves a clear signal in sediments, ice cores, and ocean chemistry. This is the onset of the Pliocene glaciation, a process that builds and stabilizes the polar ice caps that still define the planet today. Within this gradual cooling, the conditions that sustained Megalodon begin to reorganize. The change does not act directly on the animal as a simple thermal limit. Instead, it alters the structure of the ocean in ways that remove the specific environments Megalodon depends on. Sea levels begin to fall as increasing volumes of water are locked into expanding ice sheets. The broad, warm, shallow coastal seas that once bordered continents start to contract. These regions, stable and productive, had functioned as nursery habitats where juvenile Megalodon could grow with reduced exposure to larger predators and consistent access to food. As these environments diminish, the early life stages of the species lose a critical foundation. At the same time, the distribution of prey shifts. Large baleen whales, which form the primary caloric base for adult Megalodon, respond to the cooling ocean by following changes in productivity. Cold, nutrient-rich waters at higher latitudes begin to support dense blooms of krill, creating feeding grounds far from the warmer regions where Megalodon had operated most effectively. Whale populations expand into these zones, adjusting migration patterns and concentrating their biomass in environments increasingly distant from the predator that once relied on them. Megalodon carries a physiological capacity to elevate its body temperature above ambient water, a form of partial endothermy that allows activity across a range of conditions. However, this capability has limits. Sustained activity in near-freezing waters would impose a significant energetic cost, particularly for an animal with a mass between 50 and 100 tons. The balance between energy intake and expenditure begins to shift unfavorably as prey becomes less accessible within the thermal range the animal can efficiently occupy. Within the temperate zones that remain, another lineage expands its presence. The great white shark, smaller in size but more flexible in thermal tolerance, operates with a form of regional endothermy that allows effective hunting in cooler waters. Its body plan supports faster acceleration and lower absolute energy requirements, enabling it to exploit environments that are becoming marginal for larger predators. As Megalodon's range contracts, the overlap between these two predators increases, particularly in coastal areas where juvenile individuals of the larger species are most vulnerable. Evidence suggests that great whites and Megalodon shared similar dietary niches during this period. In such overlap, competition emerges not through direct confrontation between adults, but through pressure on shared food resources and potential predation on younger individuals. Juvenile Megalodon, already affected by the loss of protected nursery habitats, face an environment where both food availability and survival probability are reduced. The process unfolds over an extended interval rather than a single event. Populations begin to fragment as suitable habitats shrink. Reproductive success declines as fewer juveniles reach maturity. The distribution of individuals becomes increasingly limited, with isolated groups separated by regions no longer capable of supporting them. Genetic diversity decreases, resilience weakens, and the capacity to recover from environmental fluctuations diminishes. Across this period, the ocean does not lose productivity entirely, but it redistributes it in ways that favor different scales and strategies. Smaller, more adaptable predators persist and expand, while the largest forms encounter narrowing constraints. The apex position, once occupied by Megalodon across broad regions, becomes increasingly difficult to maintain as the underlying support system changes shape. Eventually, the population falls below the threshold required for long-term viability. The disappearance is not marked by a single boundary layer or abrupt signal, but by a gradual absence in the record, a thinning of occurrences until none remain. Megalodon does not end through direct displacement or catastrophic event. Its decline reflects a broader reconfiguration of the ocean, in which the conditions that once sustained it no longer align. Across the span already traced, a single lineage continues to appear without interruption, not always at the top, not always dominant, yet never fully removed. Sharks move through these ages without a single defining peak, instead carrying a persistence that extends across conditions that ended nearly everything else. They have passed through the Ordovician, the late Devonian, the Permian-Triassic, the end Triassic, and the Cretaceous Paleogene extinctions, each interval stripping away entire ecosystems, each one leaving sharks diminished but still present. Their survival does not rest on overwhelming strength or scale. It emerges from a set of traits that allow adjustment when conditions narrow. The cartilaginous skeleton is lighter and less resource-intensive than bone, requiring less calcium at times when ocean chemistry becomes unstable. This structure also permits flexibility in growth and movement, reducing the energetic cost of maintaining a large body. Their diets remain broad, shifting between prey types as availability changes, rather than depending on a single source that may disappear. Reproduction follows a different path than many marine organisms, producing fewer offspring, yet each one larger and more developed, capable of surviving in environments where vast numbers of smaller larvae would fail. Within modern oceans, traces of earlier forms persist in unexpected ways. The frilled shark, Chlamydocelicus anguineus, inhabits deep water, its elongated body, and multiple gill slits, recalling designs that have remained largely unchanged for hundreds of millions of years. It moves slowly through dim environments, a continuation of patterns that extend back to the Carboniferous, carrying forward a morphology that has required little alteration to remain viable. Another lineage follows a different trajectory, one defined by time itself as much as form. The Greenland shark, Somniosus microcephalus, grows at a rate of approximately 1 centimeter per year. It reaches maturity only after more than a century, with individuals verified to live at least 272 years, and possibly far longer. In these animals, a single lifespan can span events that, for most species, would represent multiple generations. They move through cold northern waters with a pace that reflects stability rather than urgency, enduring in environments where rapid change is less frequent, but conditions remain demanding. At the opposite extreme of feeding strategy, the whale shark, Rhincodon typus, reaches lengths of up to 18 meters, the largest living fish in the ocean. Its scale approaches that of extinct predators, yet its behavior diverges completely. It feeds by filtering plankton, drawing in immense volumes of water and extracting microscopic organisms. Here, maximum body size is achieved not through active predation, but through access to abundant, widely distributed resources, illustrating a different pathway to scale within the same lineage. Between these forms lies a spectrum that extends across more than 500 species. Some measure only 17 centimeters, occupying niches within the deep ocean where light barely penetrates. Others patrol open waters or coastal shelves, adapting to conditions that vary in temperature, depth, and productivity. This diversity is not a residual fragment of a once dominant group, but an active and continuing presence shaped by repeated cycles of expansion and reduction. In earlier sections, apex predators rose to prominence, exerted influence across entire systems, and then disappeared as conditions shifted beyond their range. Sharks participated in those systems at multiple levels, sometimes occupying the highest position, more often existing alongside or beneath other dominant forms. Their continuity reflects an approach that does not depend on holding the apex position at all times, but on remaining adaptable enough to persist when that position is lost. Through this lens, the story revolves not around a single peak, but around endurance. The ocean continues to change, its structure reorganizing in response to forces that operate far beyond any one lineage. Within those changes, sharks remain, not unchanged, but never entirely removed, carrying forward a presence that spans the full length of the narrative. At the present edge of this long sequence, the highest position in the ocean is occupied by an animal that does not resemble the dominant forms that came before it. The orca, or Cenos orca, moves through every ocean basin, from equatorial waters to the edges of polar ice, and at no stage in its life does it face a consistent natural predator. Its place at the top is not defined by size alone, but by a combination of coordination, perception, and learned behavior that reshapes how predation operates in the modern sea. Orcas do not hunt as solitary individuals drifting through open water. They operate in pods, structured groups that maintain long-term social bonds, each member contributing to a coordinated sequence of movement and sound. Echolocation allows them to map their surroundings with precision, resolving the position and motion of prey even in low visibility. Within these groups, behaviors are not fixed but transmitted. Techniques are observed, repeated, and refined across generations, forming regional traditions that persist over decades. In some coastal populations, individuals propel themselves onto shorelines to capture seals before sliding back into the water. In colder regions, pods generate synchronized waves that break across ice flows, dislodging resting prey into the water below. These are not isolated actions, but shared practices maintained within distinct communities. Their diet reflects this flexibility. Orcas consume fish, squid, and marine mammals, adjusting to local conditions, yet certain populations specialize to a remarkable degree. In parts of the Pacific, individuals target great white sharks, approaching from below, overturning them to induce tonic immobility and extracting the liver, an organ dense with energy, while leaving the remainder largely untouched. In other regions, coordinated groups have been observed attacking blue whales, animals far larger than any single orca, using repeated ramming and sustained pursuit to exhaust them. These interactions place orcas at a level of behavioral complexity not documented in other marine predators. Alongside them, sharks remain present, though their scale and role differ from earlier intervals. The great white shark, Carcharodon carcharias, reaches lengths of approximately 6 to 7 meters, powerful within its environment, yet smaller than several extinct predators described earlier. Its bite force, estimated around 4,000 newtons, is effective for its prey, but does not approach the upper limits seen in older lineages. It operates as a solitary hunter, relying on ambush and acceleration, maintaining a position within the upper tiers but not occupying the absolute apex across all regions. When placed within the broader context, the modern ocean's predator structure appears narrower than in earlier periods. During the Jurassic and Cretaceous, multiple large predators coexisted at comparable scales, occupying distinct niches that together formed a layered hierarchy. In the Miocene, abundant whale populations supported predators of extraordinary size, including forms that rivaled or exceeded anything alive today. Those conditions depended on extensive warm seas, high productivity, and stable nutrient cycles that sustained large prey populations across wide regions. The present ocean operates under different constraints. Continental configurations have shifted, shallow inland seas have receded, and global temperature gradients have introduced stronger distinctions between regions. Productivity remains high in certain zones, yet it is less evenly distributed, concentrating energy into narrower bands. The apex tier reflects this structure, with fewer species occupying the highest level and fewer individuals sustaining that position at large scale. In recent centuries, an additional influence has entered this system. Human activity has altered ocean conditions through fishing, habitat modification, and climate change, affecting both predator and prey. Large sharks have declined in many regions, and even apex species encounter pressures that were not present in earlier intervals. The pattern that once depended solely on geological and climatic forces now includes a new factor, one that operates on shorter timescales and across the entire ocean. Within this setting, the orca holds its position, not as the largest predator in absolute terms, but as the most capable within the conditions that exist now. Its dominance reflects the present state of the ocean, shaped by a combination of environment, history, and adaptation that continues to evolve. The story rests on remains that are almost always incomplete, scattered traces preserved by chance rather than design, and from these fragments, entire animals have been assembled with careful reasoning and measured uncertainty. Paleontology does not recover whole worlds intact. It gathers pieces, compares patterns, and extends lines of inference outward from what can be held and studied. Each reconstruction carries a degree of confidence, yet also a margin where the unknown quietly persists alongside the known. Consider the scale of Megalodon, often described within a range of 15 to 20 meters. That range is not a matter of preference, but a reflection of genuine scientific debate. No complete skeleton has ever been recovered because cartilage, the material that formed most of its body, does not fossilize with the reliability of bone. Teeth endure, large and numerous, and from them proportions are inferred by comparison to living sharks. Those comparisons are grounded, but they are still comparisons, and small differences in scaling ripple outward into meters of total length. The same careful uncertainty follows other figures in this sequence. The immense bite force attributed to the pliosaur, often called Predator X, approximately 33,000 newtons, emerges from biomechanical modeling applied to a partial skull. Muscle attachments are estimated, leverage is calculated, and the resulting figure stands as the most rigorous estimate available. Yet it remains contingent on assumptions that could shift with the discovery of additional material. A single new specimen, preserving a detail not yet seen, could refine or alter that number in meaningful ways. Livyatan melvillei, a predator that once moved through Miocene seas, is known primarily from a skull and a small number of teeth. Its total length is extrapolated by comparing skull proportions to those of modern sperm whales, animals that differ in feeding strategy and anatomy. The estimate is informed, not arbitrary, but it is still an extension beyond direct evidence. The body that carried that skull is reconstructed in outline rather than preserved in full. Even the distribution of fossils introduces its own quiet bias. The record is richest in regions where sediment accumulates, along continental shelves and shallow seas where burial is more likely. Vast stretches of the ancient ocean, especially deep basins far from land, leave little trace. The Panthalassic Ocean, which once surrounded Pangaea, covered immense areas, yet contributes only faint signals to the fossil record. Predators that lived and died there may have left no recoverable remains, their existence unrecorded except in the possibility that such niches were occupied. Within that absence, there is space for entire lineages that remain unknown, apex predators that may have risen and fallen without leaving a single identifiable trace. The structure of ecosystems suggests that such roles were likely filled, yet without fossils, they remain beyond reconstruction. The narrative that has unfolded is therefore both detailed and incomplete, a map drawn from available points with wide regions left uncharted. Recent decades have shown how quickly that map can change. The formal recognition of Leviathan in 2010, the description of Predator X in 2012, the resolution of Helicoprion's spiral jaw through CT scanning in 2013, and isotopic studies in 2022 refining Megalodon's position within the food web all emerged from material that had existed for years, sometimes decades, before being fully understood. Specimens rest in collections, labeled and stored, awaiting new techniques or new perspectives that will reveal what was previously hidden. There is a quiet implication in that pattern. The next adjustment to this story may already exist, embedded in stone or resting in a drawer, its significance not yet recognized. Each discovery does not replace the narrative, but refines it, adding detail, correcting scale, and occasionally altering the relationships between its parts. The ocean's history, as it is understood now, remains open, shaped by evidence that is still being uncovered, interpreted, and slowly assembled into a clearer view. From a distance wide enough to hold the entire sequence at once, the individual forms begin to dissolve into something more consistent, a set of repeating structures that persist even as the animals themselves change. Across hundreds of millions of years, through intervals of expansion and collapse, the same underlying movements appear again and again, quiet in their regularity, shaping outcomes long before any single lineage comes into focus. The first pattern is absence that does not last. Each time the upper tier was cleared, whether gradually or in abrupt pulses, the vacancy remained only briefly in geological terms. A few million years passed, sometimes less, and a new lineage expanded upward into the open position. The identities shifted from armored fish to reptiles to mammals to sharks, yet the structure reasserted itself with remarkable consistency. The ocean does not sustain a prolonged emptiness at its highest level. Given time and sufficient stability, something always grows into that space. The second pattern lies in how these lineages ended. No apex predator in this sequence was displaced by a direct rival of equal scale. There were interactions, overlaps, and moments of shared dominance, yet the final removal always came from beyond the competitive field. Forests altered nutrient flows and destabilized entire systems. Volcanism changed atmospheric composition and ocean chemistry. Impacts from space blocked sunlight and collapsed the base of the food web. Cooling cycles rearranged currents and habitats. The forces that ended dominance operated at scales larger than any predator, reshaping the conditions that made that dominance possible. A third pattern becomes visible in the alignment between predator and environment. Each dominant form reflects the structure of the world that supported it, not as a generalist presence, but as a precise expression of available energy, temperature, and habitat. Where reefs were extensive and productive, heavily armored predators emerged. Where shallow, warm seas expanded across continents, large reptiles with powerful locomotion systems thrived. Where whale populations concentrated in warm oceans, a giant shark could persist at extraordinary size. Alter the underlying conditions, even gradually, and the traits that once conferred advantage begin to lose their function, not through failure, but through mismatch. Alongside these rises and endings, a quieter continuity persists. The fourth pattern belongs to those that did not dominate. Survivors tend to be smaller, more flexible, less dependent on a narrow range of conditions. Their skeletons require fewer resources. Their diets encompass a broader range, and their reproductive strategies favor fewer, more capable offspring. When environments shift rapidly or degrade, these traits allow persistence where specialization cannot. The lineages that endure through multiple collapses often occupy peripheral roles in stable times, expanding only when the system opens. The fifth pattern unfolds over longer spans, extending beyond the immediate aftermath of extinction. Recovery is neither quick nor restorative in a simple sense. It proceeds over millions of years, rebuilding complexity layer by layer. The resulting ecosystems differ from those that preceded them, sometimes profoundly, with new relationships, new dominant groups, and new pathways for energy flow. The apex position is reoccupied, but not by a continuation of what came before. It is filled by something that emerged from the margins, shaped by conditions that no longer resemble the earlier world. Together, these patterns describe a continuity that runs beneath every transition in this history. They are not tied to specific species or singular events, but to the broader dynamics of the ocean itself, a system that reorganizes in response to forces both internal and external. The present moment, with its own pressures and alterations, sits within that same framework, another point along a sequence defined not by permanence, but by change that unfolds at scales far beyond any individual life. Across the present surface of the ocean, the changes do not arrive as a single event, but as a series of overlapping shifts, subtle at first, then accumulating into something that resembles the early stages of patterns seen before. The structure is familiar when placed against the long arc of ocean history, yet one element within it has no precedent in any previous interval. Temperature is among the clearest signals. Since 1900, average ocean surface temperatures have risen by approximately 0.9 degrees Celsius, a shift that continues to accelerate. In earlier transitions, warming and cooling unfolded over thousands or millions of years, allowing ecosystems time to adjust, migrate, or fragment gradually. The current rate compresses those changes into decades, altering circulation patterns, redistributing nutrients, and shifting the boundaries that define where species can exist. Warm water expands, pushing into regions that were once cooler, while cold-adapted systems contract or disappear. At the same time, the chemistry of the ocean is adjusting in response to increasing carbon dioxide. As CO2 dissolves into seawater, it forms carbonic acid, lowering pH and altering the availability of carbonate ions that many organisms require to build shells and skeletons. The rate of this change is estimated to be far faster than during previous major disruptions, including the event at the Permian-Triassic boundary. Organisms that depend on stable chemistry encounter conditions that move beyond their capacity to adapt within a single generation. Within this shifting environment, the upper levels of the food web show measurable decline. Apex predators, which once maintained balance across vast regions, have been reduced significantly over a relatively short span. Great white shark populations in parts of the North Atlantic are now estimated in the low thousands. Oceanic white-tip sharks, once common in tropical waters, have declined by approximately 98% in the Gulf of Mexico since the mid-20th century. Across the global ocean, overall shark numbers have fallen by an estimated 71% since 1970. These figures represent not isolated cases, but a broad contraction of the highest tier. The effects of that contraction extend downward through the system. In areas where large sharks have diminished, populations of rays have increased, placing greater pressure on shellfish communities and altering coastal ecosystems that depend on those species. In other regions, disruptions to orca populations have been associated with changes in prey dynamics that ripple through kelp forests, environments that stabilize coastlines and store carbon. These shifts do not occur in isolation, but as interconnected responses, each change influencing another in a chain that reflects the structure of the food web itself. Across the entire sequence of ocean history, the role of apex predators has remained consistent. They are not incidental presences, but structural components, shaping behavior, distribution, and energy flow at every level beneath them. When that top layer is altered or removed, the system does not remain stable. It reorganizes, sometimes gradually, sometimes abruptly, but always in response to the absence of that regulating influence. What distinguishes the present interval from all previous ones is not the pattern of disruption, which echoes earlier events, but the source. For the first time, the changes are being driven primarily by a single species operating outside the ocean itself. This influence extends through extraction, habitat alteration, and the release of greenhouse gases that affect both temperature and chemistry. Unlike volcanic provinces or orbital cycles, this driver is capable of perceiving its own effects, measuring them, and understanding their implications. The ocean continues to respond as it has in the past, adjusting to new conditions through shifts in composition and structure. The trajectory remains open, shaped by forces that are still unfolding. Within that unfolding, the same patterns that governed earlier eras are present, now intersecting with a cause that has no direct counterpart in the previous 450 million years. There is a moment, if the sequence is allowed to settle without interruption, when the individual forms fade slightly, and what remains is the fact that each of them existed in full, not as specimens or diagrams, but as living animals moving through real water under real light. Each hunted, missed, fed, healed, and continued, occupying a span of time that was complete in itself, even if it now appears as a brief interval within a much longer record. A pliosaur rising through a Jurassic sea did so beneath a sky that, in its broad arrangement, would be recognizable now. The stars were already fixed in patterns that change only over immense durations, and 160 million years is not enough to rearrange them beyond recognition. The light that reached the ocean's surface then traveled across the same distances, arriving from the same directions, falling across a different world that nonetheless shared that distant continuity. Earlier still, in the Devonian, an armored predator opened its jaws on a planet that had already accumulated billions of years of history. The Earth at that moment was not young or forming, but already layered with prior worlds, each one having risen and altered conditions before giving way to another. The creature itself was not aware of that depth of time, yet it existed within it, as every organism does, shaped by processes that extend far beyond any single lifespan. Deep time carries a texture that differs from ordinary narratives. It does not organize itself around isolated events or singular moments, but around the gradual shaping of conditions. Temperature shifts, atmospheric composition, continental movement, and ocean chemistry combine over long intervals to define what forms of life can emerge. Within those constraints, certain structures become viable, others fade, and the system moves forward without intention, guided by the interplay of physical and biological processes. Each apex predator encountered in this sequence can be understood as a response to those conditions. It is not a final stage or an endpoint, but a configuration that fits a particular set of circumstances. When those circumstances change, the configuration no longer aligns and another takes its place. The continuity lies not in the persistence of any one form, but in the ongoing process that produces them. This perspective places all of these animals within the same framework, regardless of their scale or familiarity. The early cephalopod moving through Ordovician waters, the armored fish of the Devonian, the reptiles that later dominated the seas, and the large shark that followed each represent solutions that worked for a time. Their existence was neither inevitable nor permanent, but contingent on the state of the world at that moment. The same framework extends into the present. The conditions that define the current ocean and the broader environment that supports it have produced a particular set of organisms, including those capable of observing and reconstructing this history. These observers are themselves shaped by a stable interval, an interglacial period with specific temperature ranges and atmospheric composition that allow for complex social structures and sustained reflection. That interval is part of the same sequence, subject to the same patterns that have governed earlier transitions. The apparent stability that defines it exists within a larger context of change, where shifts in temperature, chemistry, and geography eventually alter the conditions that made that stability possible. The processes that produced previous worlds continue to operate, sometimes slowly, sometimes with greater acceleration. Seen in this way, the sequence carries a weight that is not tied to any single creature or moment, but to the continuity of change itself. Each life that unfolded did so completely within its own frame, while also being part of a larger progression that moves beyond individual experience. The ocean, across its history, has never remained fixed, and the forms that inhabit it have never been permanent fixtures, but expressions of conditions that are always, eventually, replaced. Far beyond the span of any recorded memory, the ocean continues forward, carrying with it the same underlying processes that have shaped every transition described so far. Its duration extends across 3.8 billion years, a continuity that has absorbed extinctions, reorganized ecosystems, and replaced entire dominant lineages without interruption. Each event that once defined an era now exists only as a layer within that longer persistence. If the timeline is extended outward, the surface of the planet begins to rearrange once more. Over the next 100 million years, tectonic motion will shift the continents into new alignments, altering coastlines, currents, and the distribution of shallow seas. Regions that are now elevated may sink beneath water, forming new basins of high productivity, while others may rise and close existing connections. The Atlantic Ocean will continue to widen as seafloor spreading proceeds, while the Pacific gradually contracts. Inland seas may return in places that are currently dry land, creating environments that have not existed for tens of millions of years. Within those future oceans, the structural position at the top of the food web will remain, as it always has. The identity of the organism that occupies it cannot be specified in advance, yet the pattern suggests its origin. It is unlikely to arise from a lineage that is already dominant at large scale. More often, the source lies among groups that persist at the margins, maintaining flexibility and diversity without occupying the highest tier. Given time and the right combination of conditions, such lineages expand, adapt, and eventually fill the open space. One possibility lies with cephalopods, a group that has persisted since early intervals and once held the highest position in the ocean. Today they exist as squid, octopus, and nautilus, occupying a range of ecological roles without reaching the scale of past apex forms. Their capacity for rapid growth, behavioral complexity, and short generational turnover provides a foundation for future change, should environmental conditions favor their expansion into larger and more dominant forms. Another possibility exists among fish lineages that remain less visible, particularly those inhabiting deeper or colder regions where fossilization is rare and observation is limited. Within these groups, evolutionary pathways may already be developing that are not yet apparent in the present record. Given sufficient time, such pathways can lead to forms that occupy roles far removed from their origins. There is also the potential for configurations that have no clear precedent in current life. Throughout this sequence, entirely new body plans have emerged when conditions shifted in specific ways, producing predators that would have been unfamiliar to earlier ecosystems. Future oceans may generate comparable novelties, forms that combine traits in ways not currently observed, shaped by environments that differ from those of today. Throughout all of these possibilities, the ocean itself remains unchanged in its fundamental character. It does not retain the presence of previous dominant forms, nor does it accumulate memory in the way individual organisms do. The large predators that once moved through its waters have left traces in sediment and rock, but their absence does not alter the ongoing processes that continue to shape the system. The cycle of occupation, transformation, and replacement proceeds without pause. Apex positions are filled, environments shift, and those positions are vacated and filled again. This continuity does not depend on any single lineage or event, but on the persistent interaction of physical conditions and biological responses that define the ocean over long timescales. Looking ahead, the same structure remains in place, extending beyond the present moment into intervals that will not be directly observed. The forms that will eventually dominate are not yet known, but the framework that will produce them is already active, guiding the future as it has guided the past, through a sequence that continues without a defined end. At this moment, the ocean extends across approximately 71% of the planet's surface, a continuous body of water that reaches down to 10,935 meters in its deepest known point within the Mariana Trench, holding within it an estimated 700,000 to 1 million species. Most of those forms have not been formally described, existing beyond the reach of systematic observation, known only through scattered encounters or indirect traces that hint at a far greater diversity than has been cataloged. Below 1,000 meters, sunlight no longer penetrates, and the environment shifts into a different regime entirely. Pressure rises beyond 100 atmospheres, temperature stabilizes near freezing, and the surface world becomes distant, separated by layers of water that filter out both light and motion. Within this space, entire ecosystems persist that have never been directly observed in their full complexity. Organisms move, feed, reproduce, and die in conditions that remain largely inaccessible, shaped by gradients of chemistry and energy that differ from those above. Among the largest inhabitants of this darkness is the giant squid, Architeuthis dux, an animal that can reach lengths of at least 13 meters and carries eyes up to 30 centimeters in diameter. These eyes are not adapted for brightness but for sensitivity, capable of detecting faint disturbances in a field of near total blackness. They are tuned to the flashes of bioluminescence and the movement of large bodies through the water, particularly those of sperm whales that descend from the surface to hunt at depth. The interaction between sperm whales and giant squid represents one of the remaining large-scale predator and prey relationships operating beyond direct human observation. It unfolds in an environment where pressure compresses, light does not travel, and sound becomes the primary medium of perception. Encounters leave marks, circular scars on whale skin, impressions of tentacles and hooks, evidence of contact that occurred far below where it could be witnessed. Elsewhere, in the same depths, movement can be measured in slower rhythms. A Greenland shark, capable of living for centuries, passes through cold water at a steady pace, its growth extending over long spans of time. Individuals alive today may have begun their lives centuries ago, continuing through conditions that change gradually around them, their presence linking distant moments within a single, continuous lifespan. Above and below, across layers of sediment and water, the remains of earlier worlds persist. The forms that once occupied the highest positions in previous oceans are now embedded within rock, distributed through limestone, shale, and chalk, their structures compressed and preserved. Teeth, fragments of bone, and impressions remain as physical records, while the material that composed them has been incorporated into new systems, circulating through water and living organisms. The ocean retains these layers without distinction, holding both the present and the past within a single connected system. The processes that formed earlier environments continue, reshaping materials and redistributing energy, linking the remains of former predators with the organisms that now move through the water above. There is no fixed endpoint within this sequence. The ocean persists as a dynamic system, adjusting to changes in temperature, chemistry, and geography, maintaining continuity through transformation rather than stability. Its scale extends beyond immediate perception, and its processes operate across intervals that exceed individual experience. In its current state, the ocean remains active, populated, and incomplete in the sense that it continues to evolve. New forms will emerge, existing ones will change, and the structure of its ecosystems will shift in response to conditions that are still developing. The continuity that has defined its history remains in place, carrying forward into intervals that extend beyond the present, with no indication of a final conclusion.